Okay, here we want to work on exponential functions. Okay, our goal when we solve the exponential functions is to obtain the same base on both sides of the equation. Okay, so and we want to basically turn an exponential equation into a simple algebraic equation. So here we have 4 to the 2x minus 5 is equal to 64. So what we want to see is there any way that we can write 64 with a base of 4? And we can. So we will rewrite this as 2x minus 5 is equal to 4 to the third power, because we know 4 to the third power is 64. Now, once we have the same base, we go to the next level, and we have 2x minus 5 is equal to 3. This is what we mean. We changed an exponential equation to a basic algebraic equation. And of course, we solve this 2x minus 5 equals 3. We add 5 to both sides. 2x is equal to 8, and therefore x is equal to 4. That's how we solve a basic algebraic equation. So now, when we look at this, and we've talked about having the same base on both sides, now we can look at one where we have 4 to the x minus 8 is equal to 32. So once again, we have to see, can we write 32 with a base of 4? No, because 4 to the first power is 4. 4 squared is 16, and 4 to the third power is 64. But we skipped over that 32. But we can have a common base of 2. So we will rewrite the 4 as 2 squared. 4 turns to 2 squared, and the 32 turns into 2 to the fifth power. So now we've still obtained our same base. So once again, we just move to the next level. 2 times x minus 8 is equal to 5. Two x minus 16 is equal to 5, because of course we have to distribute. Adding 16 to both sides. 2x is equal to 21. And once we divide by 2, x is equal to 21 halves, right here. So this is another way to solve this type of equation. Remember, our goal, just like on the last one, was to get the common base. All right. So now our last problem. I can just use this 4 to the x minus 6 is equal to 20. So once again, 4 squared is 16. 4 to the third is 64. So we can't use a base of 4. We can't use a base of 2. 2 to the fourth is 16. 2 to the fifth is 32. So there's no way that we can use a common base. So in this case, we have to take the log of both sides. All right, we have to take the log of both sides. Okay. Now, according to the rules, and we have to go over this, once you take the log of both sides, that brings our exponent down. So now we have x minus 6 log 4 is equal to log 20. Remember that rule, that's the old pre-calculus rule, where anytime you take the log of a base with an exponent, we're allowed to bring that exponent down. Now we need to distribute. That's going to be x log 4 minus 6 log 4 is equal to the log of 20. Now the goal, we were able to do this much easier when we were able to have the same base on both sides, but the goal is still to get x by itself. So our next step is negative 6 log 4. We need to move to the other side of the equation. So that's going to be log 20 plus 6 log 4. All right, so we're just going step by step. Once again, this negative 6 log 4, once we moved it to the other side of the equation, it became positive 6 log 4. And our goal here, once again, is to get this x by itself. So what do we need to do? Divide both sides by log 4. This cancels out, so our final answer will be log of 20 plus 6 log 4 divided by log 4. Now you can easily check this on a calculator and let the calculator do the calculations and put it back into our equation and just to confirm our answer. But this is how we solve a problem, an exponential equation, when we are unable to get the same base on both sides.